Swayam Prabha. Digital India. Educated India.
And then I'm introducing the next speaker who is online. Jungyang Li from Taipei University of Technology. So he's going to make a presentation on the design of hybrid power systems considering load shifting and parametric uncertainty. So the floor is yours. And you have 20 minutes, so keep your mic or the loudspeaker open so that you hear me if I'm asking you to stop. Okay?
Okay, thank you. Okay, thank you very much, Mr. Chairman, and good afternoon, ladies and gentlemen. This is Lee from National Taipei University of Technology, and this work is done by my student, Mr. Zhen, and myself. And the title is Design of Hybrid Power Systems Considering Load Shifting and Parametric Uncertainty. So for this presentation, firstly, I will give you some background, and I will define the problem, and I will mention the main feature of this work. And yeah, again, I'll define the problem and show you the superstructure. Based on the superstructure, we formulate the mathematical model for the optimization. And then I will present a case study to demonstrate the use of the model and the optimization approach. And finally, I will conclude the presentation with a few remarks. So currently, many countries have announced long-term goals to achieve net zero emissions by 2050. And this is to tackle climate crisis and to avoid the worst effects of climate change. And in the net zero by 2050 scenario, you can see that in the diagram below, renewables, or in particular, wind and solar and bioenergy will play a key role in the planning. So to increase the use of renewable energy, hybrid power systems, which consist of 2 or more generation sources to provide electricity to low demands, can be used to provide electricity in a more efficient and reliable manner. In the design of hybrid power systems, we can consider load shifting to shift loads from peak hours to off-peak hours to reduce the electricity cost. And we can also, by doing so, reduce the requirement for storage, for any storage capacity, and to reduce the storage cost. So compared to the previous work where the load shifting strategy is determined by heuristics, and the previous works are more like scenario analysis, we have some different approach in this work. We incorporate load shifting in the model formulation, so our model will be able to optimize load shifting and the system design at the same time. Okay, so in this work, we consider the problem given given here. We consider a grid-connected hybrid power system with a set of power sources and a set of power demands. And also, because of the intermittency of renewable energy, we will also consider a set of energy storage options. For the power sources, if you can see on the right-hand side, we can, in general, we can consider conventional and renewable sources, although in this work, we will be focusing on renewable energy. And for the demands, they are flexible demands for which we can shift the operating time, provided that it doesn't affect the services to be provided. And we have also fixed demands for which we have to operate them at the planned times. And we also consider power import and export in case of a surplus or deficit of power, because this is a grid-connected hybrid power system. And the objective is to determine the optimal hybrid power system design and load shifting strategy. So this is the superstructure on the right-hand side. Based on this superstructure, we formulated our mathematical model. And again, in the superstructure, we consider a set of power sources. We consider a set of power demands and a set of a set of energy storage systems. And this superstructure considers all the connections between the components in the system. So the model formulation would be based on the superstructure and consists mainly of energy balances, the power sources, power demands, and energy storage systems. But because of the time limitation, I cannot walk you through these equations. So the details can be found in our previous work and will be just skipped here. And I'll move to the load shifting constraints. Here in our formulation, we define two binary variables to indicate the times, the start time and operating time of the demand. So with these binary variables and constraints, we can determine at which point in time the demand starts to operate and lasts for the duration until the end of operation. So using these constraints, we can consider load shifting while designing our hybrid power system. So to optimize the hybrid power system, we consider the objective functions. Also, we consider two different approaches. We have sequential and simultaneous approaches. For the sequential approach, in order to compare the result with the literature, we consider two sequential approaches. The first one, sequential A, is we minimize the power input first, and then the energy-related storage capacity. And then in order to allow more details in design to be considered, we have sequential B, the second sequential approach. We minimize the annual electricity cost and the annualized storage cost. Alternatively, for simultaneous optimization, we can also minimize the total annual cost, which is the sum of the electricity cost and the storage cost and the power generation cost. Okay. So to demonstrate the use of the model, we have a case study taken from the literature, and this case study have full renewable energy sources, which are wind, biomass, hydro, and solar, for 8 power demands. In this case study, we assume that a sodium-sulfur battery can be used for energy storage. Then we consider two scenarios. The first scenario is without power input. The second scenario is with power export. So we can compare the results of the scenarios to see the effect of power export. And we also performed sensitivity analysis to see the effect of the export power price. We changed the value of the export power price to see the change in the results. And also we have Pareto analysis and fuzzy optimization to explore the trade-off between cost and emissions, and also to address uncertainties in parameters such as cost and emission factor. So for this case study, we have the data for power sources, power demands here, and the cost and technical data. And then this is the results for the scenario 1. We can compare the shifted demand profile with the original demand profile, and we can see that the load shifting strategy determined by a sequential approach will reduce the mismatch between demand and generation, and the strategy determined by the simultaneous approach reduces the peak demand. So these shifted demand profiles are able to keep down the storage. These shifted demand profiles are able to keep down the storage profile. So the results will have a smaller storage capacity and a lower storage cost. And here is the summary of the result of scenario 1, and we can see that the sequential B considers electricity tariffs in peak and off-peak hours. So you can see that in the results, we have more power input in off-peak hours than in peak hours, compared to sequential B, where we didn't consider electricity tariffs. So in the results of sequential B, the electricity cost is lower. And also we can look at the result of simultaneous approach. In this case, we see that in the results, only wind energy is used, and the power supply would, the optimization would prefer the use of grid power instead of renewable energy from solar, hydro, and biomass. This is because in this case, the current electricity tariff is lower than the generation cost of these sources. So we can observe this from the results. And then we consider scenario 2, where we allow power export, and we assume that the export power price is equal to the electricity tariff in off-peak hours. So with this low export power price, we have the same results as in scenario 1. And here we compare the results from simultaneous approach for scenarios 1 and 2. And we can see that the total cost are the same, although there are different amounts of power input and export. This is because the current export power price is too low. So power export doesn't make any profit. So that is the reason we continue the analysis. We had a sensitivity analysis to see the effect of export, to see the effect of export power price on the system design. So in this page, you can see that with increasing export power price, we can see that the total cost decreases and the total generation capacity increases. And also we see that the increases in power input and power output. But we need to be careful here, because if a very high export power price only leads to a trivial solution, because in that case, all the power generated from renewable energy is only exported to the grid. So we need, here we just see the effect of export power price, but in practice, we have to know, or we have to find or determine an appropriate export power price. And then we have a Pareto analysis to explore the trade-off between cost and emissions. And we can see that for different export power price, we have the Pareto frontiers. Okay, so these are this is to provide alternative solutions for decision maker when both economic and environmental objectives are to be considered in design. And from these Pareto optimal solutions, we observe that at the same emission level, the higher the export power price, the lower the total cost. And this finding is consistent with what we found in the sensitivity analysis. Okay. And then finally, we performed fuzzy optimization to address uncertainties, and also we used fuzzy optimization to find a compromise solution considering both economic and environmental objectives. So we here have fuzzy model 1 and fuzzy model 2. Fuzzy model 1 is to provide a compromise solution considering the trade-off excuse me, Fuzzy model 1 is to provide a compromise solution considering the trade-off between cost and emissions. And we can see that for two actual power prices, the fuzzy model 1 solution lie on the Pareto frontier. That means this solution is one optimum solution, and that as a result of the compromise. And fuzzy model 2 considers uncertainties. Here we assume there are uncertainties in the cost coefficients and the emission factor. And we assume fuzzy ranges for the uncertain parameters to be plus and minus 10% of the mean values. Okay, so we performed fuzzy optimization, taking into account the uncertainties, and we have the solutions on the diagram. As you can see, the triangles here represent the solutions for the solution to fuzzy model 2. And you can see that these fuzzy 2 solutions are more conservative and suboptimal, as they are located in the upper right of the Pareto frontier. So so these are the fuzzy optimization results, and we can see that we can address uncertainties and cost emissions trade-offs using the model. Okay, so to conclude the presentation, in this work, we developed the mathematical model, the optimal hybrid power system design with load shifting. And through the case study, we can see from the results that load shifting can reduce the electricity cost and the total cost. And grid power will be used instead of biomass, hydro, and solar energy if the electricity tariff is low. And increasing the export power price can increase both power import and output and export, sorry. The trade-off between, we have performed Pareto analysis and fuzzy optimization to explore the trade-off between cost and emissions, and also to address parametric uncertainties. In future work, we will consider seasonal changes in supply and demand. So there will be a multi-period scenarios, and we will also incorporate how to act technologies for energy storage and utilization in the system design. Okay, so that is our presentation. Thank you very much. And if you have any questions, I'll be very happy to answer.
Thank you very much, Professor Lee, for this presentation. So before we upload, I'm going to ask the audience if there are questions. Yeah.
Okay. Hi.
Okay, sorry. Yeah.
Just to understand about this power import. So all these importers are from individual or from any power supply player, because the concern is that if, let's say, for example, about individual from household, then should be okay. If, let's say, we have a different party of power importers, so how to handle in terms of the power consumption from the main power supplier that being supplied is they can continuously charge for all the users. So just to understand about reliability of all these power importers. All right, thank you.
Okay, thank you for your question. Currently, we haven't considered the reliability of the electricity supplier, and we are still in the preliminary design stage. So here, the more important thing is we have to know the capacities of the system and the power ratings or the requirement of export power. So here we assume that the system can be applied for household or an industrial plant. So in different cases, yeah, we will have different electricity sources. So like in this case study, it is for an industrial plant. So we assume that there is a centralized utility system that is able to provide electricity to the plant. And we also assume that the utility system is reliable. Yeah, but as you mentioned, reliability should be an issue to be considered in our future work. Thank you.
Thank you. So I have another question there.
Yeah, so this is to compare the simultaneous solution with that of sequential. So if you see in the simultaneous solution, you have the storage 0, right? Which is like storage is always getting 0.
Yes,
Yeah.
yes.
So the question is like, if you use a weighted sum, like if you see in the simultaneous, the objective function, you have weighted, you used equal weights for all the three, the storage cost, the electricity cost, and the other one, the generation cost. But you can allow storage cost to be of a lesser weight than the total cost. Then I mean, you may reduce the total cost while allowing some storage, because we are not using storage, right? So do you think that can reduce the total cost?
Yeah. Actually, we have to further perform some other sensitivity analysis about the cost coefficients. For the current cost data we used, the electricity tariff, I mean, the cost of the grid power is lower than generation cost from renewables and also lower than the storage cost. So in the simultaneous approach, the objective function is to minimize the total annual cost. So the optimization will find the way that minimize the cost. And in this case, to use grid power instead of renewable energy is that solution. So if in this case, we use less renewable energy and we also have less need, because we use less renewable energy, so we don't have the need for any storage. So that is why the solution looks like that. And yes, like you said, if we change the cost parameters, like in another sensitivity analysis, we may have different results because of the different relative costs. Yeah.
Okay, thank you.
Thank you very much. Sorry, but I have to switch to the other one because we are already quite late. So I would like first to thank you again, Mr. Lee, for your presentation. So I guess that we can applaud.
Thank you.
And yeah, thank you for participating.